Hello and welcome to the latest session for our OptiSystem software. My name is Joshua Donald and I'm the Photonics Applications Engineer here at OptiWave, and I'll be assisting your host, Ahmed Attia. The webinar today will be on vibration sensing with a focus on PHI OTDR. We will have a Q&A period at the end of the hour-long presentation, so feel free to go ahead and use the questions panel and type in any questions you have in there, and we will answer all of the questions at the end of the presentation. Now, over in the handout section, you'll find the PDF that's used in the presentation. Feel free to download and use that at any time. And lastly, we'll be recording the webinar and emailing the link to everybody an hour after the presentation. With that said, let's get the webinar underway. I would like to introduce your host, our Director of Optical Systems, Ahmed Attia.
Hello, everyone, and welcome to this webinar. Today's webinar, we're going to talk about sensors in general and in OptiSystem, and then we're going to focus on PHI OTDR theory and application in OptiSystem. Okay, so the webinar will include some introduction about the sensors in general, and then we're going to talk about the component library of OptiSystem, which includes all the sensing components. And then we're going to focus again on the PHI OTDR as a vibration sensor, which we're going to talk about the parameters in the component, how we set the parameters, and then the possible results which you can view using the interrogator. Then we're going to show you a live demonstration of these components, and we're going to open for a question and answers. Okay, so in this slide here, we're going to show you the different like block diagram of different implementations of fiber sensors, where we're going to concentrate on the sensor device and the monitoring station. So typically, we have the monitoring station and the sensor could be co-located at the same place or could be away from each other. For example, in this configuration here, we have two sensors far away from the monitoring station, which is located at one side of the system. And then we have fiber, which carries the sense information to the monitoring station. Now, the sensor could be far away from the monitoring station, so we need to use optical amplifiers to amplify the signal, which can be used like, for example, semiconductor amplifiers or Raman configuration or an EDFA to amplify the signal. The other possibility for implementation is to have a monitoring station at both sides of the system, where you have one on the east side, one on the west side, and you have one or more sensor at a different location in the system. So, and sensor technology we're going to concentrate today on is fiber sensor technology, and mainly it can be realized using, for example, grating, fiber brick grating, which this grating can be either short grating, which will be in the range of few centimeters, or long beard grating, which is in the range of a meter or so, and tilted grating. So at this moment, OptiSystem supports the first two, and the tilted grating is under development at this moment. Also, you can use fibers as a sensor for this like vibration or temperature or pressure sensing or stress strain, whatever, using the physical characteristics of the optical fiber cable, which in this kind of application we use the relay scattering effect or the nonlinear effect, such as, for example, Raman, simulated Raman scattering or simulated Brillouin scattering. When we use the relay scattering, typically in this kind of application, we usually use it in OTDR or PHI OTDR, which we're going to concentrate also on these two technologies in this webinar. In here, I listed a few references which talks about distributed fiber sensor using the simulated Brillouin scattering and Raman scattering, just for a reference if you are interested in reading these things. Okay, now what we're going to talk here is about the component library, which has all sensor components and interrogators in OptiSystem. And this is, you can find it in OptiSystem default/sensors directory or library in OptiSystem. And this library, the sensors library, has this component, which is we call the first one is uniform fiber brick grating sensor. This is a sensor which is a bidirectional component, which means the signal can go in both directions in this component from, let's say, west to east or east to west. And this would enable the different implementation of collocation or not collocated configuration of sensors and monitoring station. The other component, which is called WDM FPG Sensor Interrogator. Now, this component is typically used in conjunction with the sensor itself to do the analysis and the calculation of the sensed signal. And show you the results. And the other component here, we call it FPG sensor. And this is a unidirectional component. So the signal can go only one direction. However, like the component, allow reflection and transmission. So this is, you can think about it, if you want to use only single FPG sensor, you can have it as collocated or not collocated. However, if you want to use more than one FPG sensor in your system, this is the component wouldn't work. Now, the difference between the uniform FPG sensor and FPG sensor component is in this component here, the FPG sensor, you can design the grating itself. It's like based on the OptiGrating software, where you would be able to design the transmission, reflection, and center wavelength of the grating. However, in this uniform FPG sensor component, these parameters are set. Like users will be set the center wavelength of the grating, set the bandwidth of the grating, and so on, and the reflection and transmission. So this is the main differences. Now, there is another component in this library which called measured optical sensor. And the measured optical sensor, it's a component which based on measured data and using the S parameters of this measured data to create the reflection and transmission transfer functions of that, let's say, component subsystem. So you can find the transfer functions S11, S12, S21, S22 from the measured data, and then use these parameters to predict certain performance of the sensing system in the future. So mainly it's used in biomedical application. And then also this directory, the sensors directory, it has the PHI OTDR sensor, which we're going to concentrate on it today, with the PHI OTDR Interrogator. Okay, so now what is the sensing capabilities of OptiSystem? What we can do in OptiSystem at this moment? The capabilities of OptiSystem is not limited to temperature sensing, stress sensing, strain sensing, water salinity, which is we demonstrated in another webinar. If you go to OptiWave website, you can see this webinar which talks about this application of the gratings for sensing applications. And also we're going to concentrate today mainly on the vibration sensing using the PHI OTDR. However, users can design their own sensors based on co-simulation capabilities of the OptiSystem. So OptiSystem has a few components, which is the MATLAB component, the Python component, the C++ component, which users can write their own codes to represent certain sensing functionality, and then integrate this design into the OptiSystem. So use the other capabilities of OptiSystem in terms of signals and modulators, lasers, and so on, and detectors like optical spectrum analyzer or interrogator. So this kind of capability in OptiSystem would enable users to not only limit themselves to what is there, but they can do their own sensors design. Okay, so in this part here, we're going to talk about why do we need to use OptiSystem as a simulating tool. So usually when you, for example, deploy a sensors in the field, there might be different environmental condition there. Could be stress, could be strain, could be temperature, for example, which it's difficult to predict the behavior of the sensor under multiple operating conditions. However, if you do the simulations in OptiSystem, you can put a single effect or multi-effect in the component, so to simulate it and see how it's going to behave, the component or the grating under these conditions. The other thing is also useful using OptiSystem for sensing application is to investigate the launching condition of the signal. So, for example, how much power, how much pulse width, what type of pulses, what is the extinction ratio, all of these parameters which you could investigate using OptiSystem and enable users to design their sensor system. The other application which can be used in this OptiSystem simulation tool is synthesizing the FPG parameters, because usually when you buy a grating, the vendors do not provide you with all parameters of the grating. So if you wanted to analyze your system, or you wanted to check the performance of the system under a different condition, it's very difficult. So what you can do is you can do, for example, some measurements, and with the simulation tool, you can adjust the parameters of the component to match the measurements, and then with that you can synthesize the FPG parameters and find all these parameters, then use it for other simulation applications. And the other application which is can be used using the interrogators of OptiSystem, and especially we're going to talk about today, is the PHI OTDR Interrogator. Is you can use experimentally measured data, and then you can analyze it using the interrogator component in OptiSystem. And we're going to show you that in the live demonstration. Now, the other advantage of OptiSystem compared to other simulating tools, for example, is it is very fast. So if you do the simulation using OptiSystem, you're going to notice that the calculation is very fast to obtain certain results, and compare it to other simulation tools. We notice, like, for example, you are talking about, let's say, for example, if you use MATLAB to simulate a PHI OTDR, the calculation may take few hours compared to, let's say, for example, 10-15 minutes in OptiSystem. So this is a very good advantage in terms of simulating time of OptiSystem. Okay, so now we're going to talk quickly about the examples or implementation of the FPG sensor in OptiSystem. So you can see there are few examples in OptiSystem example library located at this location under the user's name, user's name, documents, and then OptiSystem, let's say the version right now, which is currently available in the market, 16.1 samples. And then you can go to the OptiSystem sensor system library here. You double click on it, and then you have different applications in here. Today we're going to talk about PHI OTDR concentration, but here the FPG sensor, different examples you can find using different configurations. Okay, so now in this example here, quickly we talk about using the uniform fiber brag grating at different locations, which are separated by certain length of fiber. And each location you have the grating at different center wavelength, and this would be the mark for that location. So because you use different wavelengths, you can basically define that location with that wavelength. Now, based on the environmental condition in here, you can have the wavelength, the center wavelength shifted. It depends on the temperature, depends on the stress, depends on the strain conditions. This example, again, you find it in the example library. Now, the other example also you find in example library, quickly we can talk about it, is the implementation of the grating inside a loop mirror, zigzag loop mirror. And in this configuration, by adjusting the phase inside the loop, you can have the signal, monitored signal, either on the east side or the west side or both sides. So this is one advantage of this design. Okay. In this part here, we're going to talk about an implementation which is going to be coming in OptiSystem 17. And this is an OTDR implementation. So just quickly to show you what is going on in the sensor library here about OTDR implementation. So the concept depends on transmitting pulses into the fiber under test. And this fiber under test could be different fiber types, with different cores, different numerical aperture, different attenuation. So the parameters of the fiber, each piece of fiber, users will be able to set it. Then they can simulate, for example, a splice between the fiber pieces or a connector between fiber pieces. Different types of connectors is either planar connector or APC connector, angle connector. And then also they can take a look at the end termination here, if it is rough termination or cleaved termination. So all of that would be coming into a component which is going to call it OTDR sensor. And this is display for the output, how it's going to look like. For example, here you're going to show the first piece of fiber, which is 300 meters. And then you have a splice here after that. And then you have another piece of fiber, which is 200 meters. Then you have a reflection after, which is FCBC here, which is 30 dB reflection at this location. And then another fiber piece, which is 500 meters. And then we have a splice. And then another fiber piece, which is 300 meters, which has a hybrid connection. Sometimes users have, for example, when they connect the fiber mistake, they put the ABC with BC. And then will show you the display of the results, the reflection in that scenario. And then the last fiber piece is 200 meters, and then you have BC connection, and then the last piece is 300 meters, and the termination here shows you the last reflection of configuration. So again, it's something which is going to come up in the next release in OptiSystem 17. Now we move into the PHI OTDR theory, and we're gonna talk about the implementation of the system and talk about the component settings and the results, possible results, and then show you the live demonstration. Okay, so this is a block diagram, shows the concept. You have a laser source, a modulator here, external modulator, let's say for example, Xender modulator, and you generate pulses. These pulses are launched through a circulator directed into the fiber under test. The fiber under test, these pulses are intense, and then it's going to be reflected from different locations in the fiber using relay backscattering effect. And then the signal comes back again to the detector, which is, we call it monitoring station, and the analysis is going to happen here. Now, in PHI OTDR, what's happened is these pulses and the reflection or relay backscattering reflection is always, if you send one scan, for example, one pulse and then other pulse after and so on, every time the scans is similar, unless you have a variation, local variation somewhere, you have, for example, vibration, then the relay backscatter trace would have some kind of variation in that location. So the theory, it's based on this length of fiber. What we do, we divide it into n sections, and each section, which is delta L, equals to the length over the number of sections. And what happens is you need to make sure that this pulse spatial width has to be fitting the length of delta L to be able to address the relay scattering in that section and have accurate calculation. And then what happens next is to divide these sections into subsections, and these subsections, the width of them, we distribute them normally along and randomly along the subsection length. Okay, and then after that, what happens, we calculate the electric field of the relay scattered light in each section, and the equation would be following this equation, which is in the ith section, the backscattered electric field would depend on the electric field which is incident, and this is the E minus 2 alpha. Li is the effect of attenuation of that section in the length of Li, and then this is related to the relay scattered reflection light or field in this scenario, and it depends on the scattering coefficient Rk of the ith section, and it's going to go through the m sections here in divided inside the subsection of the fiber. Now, what's happened is in this part here, we describe the process of creating these pulses, which is supposed to be intense pulses with certain width. Again, this width spatially has to cover the section delta L to be able to to detect the variation in that section. Now, the backscattered light within this spatial width or the subsection delta L within itself is going to be interfering with each other and create interfered signal. And the intensity of the interfered signal is going to be which is the electric field square. And the summation of this equation here depends on the process of interaction between the subsections inside or random scattered sections inside the subsection delta L. Once you calculate the electric field in each subsection and then monitor that at the detector side, what's happened is you're going to have these kind of traces here. And these kinds of traces, this is the intensity which is shown in the equation before. And what's happened is these traces roughly will be exactly the same every time you send pulses into the fiber, except when there is a random or local variation or vibration in the fiber, then the traces will be different. You have some phase difference there. So what's happened in the PHI OTDR, we subtract these traces from each other and we create or we find the location of the vibration, which I'm going to describe it in the next slide. In this part of the presentation, we talk about the possible noise sources in the PHI OTDR, which are related to the laser itself phase noise, relative intensity noise. So what you like to have here, you need to be able to control how much is the relative intensity noise in the launched signal. And then you might have some kind of frequency drift in the signal, which can cause some kind of noise and phase noise into the calculation, which is the basic concept of the PHI OTDR depends on the phase. So any phase variation would cause problems and noise into the system. And then another problem, which is related to the extinction ratio of the electro-absorption modulator, in terms of you need to have the extinction ratio as high as possible to have better traces quality and sensitivity of the sensor. Now, the other issue is related to the polarization fading due to randomly changing of the state of polarization in the relay backscattered light. So what's happened is this variation of the state of polarization in each subsection is going to create some kind of noise, and this fluctuation of the polarization would cause this kind of noises in the measured signal. Okay, so going back again to the process of calculating and analyzing the data in this component, the PHI OTDR interrogator, what does it do? It always monitors the traces collected from the backscattered light, and always the variation will be similar exactly if there is no disturbances. However, if there is a disturbance at certain location, the fiber will cause phase change in the scattered light at that location. Okay, and then when you subtract these intensities from each other, then you're going to have a variation and location identification of the vibration happening at that location. Now, how can we find the frequency of that vibration? What we do, we take the FFT of the subtracted traces, and then we basically determine the frequency of the vibration at that specific location. Okay, in this part here, we're going to talk about the PHI OTDR parameters. So if you take a look at the component, you're going to have this kind of window here where you're going to set up the reference wavelength of the laser line width, the fiber length. You're going to do the simulation over it. You're going to define the fiber attenuation. You're going to define the core refractive index. You're going to define the effective area of the fiber, and then the relay backscattered coefficient. Now, the number of scattering centers, this is important because, as we said, in the subsection, you determine how many scattering centers is going to be there, and they are uniformly distributed, randomly uniformly distributed. This will define resolution sometimes affects the resolution, so you need to control this parameter sometimes up and down to be able to have better sensitivity. Now this is the relay scattering intensity file name. So what's happened is the results, the data of the simulated results are stored in a CSV file, so you can post processes if you like later on. The other window here is the second window, which is under the launch pulses tab, and this controls the pulse duration, how much is the time duration of the pulse, and which affect the spatial width of the pulses. And that's important. Again, as we said, you need to make sure that this is cover the subsection in the of the fiber. And then pulse power, you can control the power launched of these pulses, and then the repetition rate of these pulses. Next tab here is the vibration sensor control, where you determine the number of vibrations. So for example, if you want to simulate one vibration and want to look at the launching conditions, you can set one vibration or multi-vibration. In this example here, we put 3 vibrations. And once you put 3 vibrations, you have to enter a string here for the vibration locations. For the previous window, we saw the length of the fiber, and then this is the location of the vibration here at 10 meters, 20 meters, and 30 meters. Then we determine the strength of the vibration. So for example, is it weak vibration or strong vibration? You can control it from this here with the amplitude. And then you control the frequency of vibration. So what is the vibration frequency? And these parameters, the location and the frequency of each vibration is monitored using the interrogator. So we can show you the final results, how this is look like. And this is the initial phase of the of each vibration. And then this is the fiber length perturbation in the calculation. You need to do some kind of within certain certainty the calculation. Okay, and this is the simulation tab here, which is including the number of traces which you need to send. For example, you need to send 300 traces or 500 traces, 200 traces. The more traces you send, sometimes it's better because you're gonna see eliminating the noises in the system, and you could have better resolution and sensitivity of the calculation. And this is the sampling rate of the calculation. Now the interrogator, in this few slides, we're gonna show you the interrogator results, which later on we're gonna demonstrate it live to you. In this slide here, we show this is the PHI OTDR component, and this is the interrogator connected to each other. And this shows you how is the subtraction of the traces would look like, which determines basically the location of the vibration. And if you see here, there is 2 tabs here. One of them is called the power, which shows you the location, and the other one is the frequency, which shows you the frequency of the vibration, the amount of the frequency of the vibration. In this example, it's demonstrating one single vibration, which is 100 hertz at 20 meters. In this example, we show 2 vibrations, and these vibrations are with the amount of 100 hertz for 100 hertz and located at 20 meter and 40 meters. So this is the location picture, and this is the amount of frequencies. As you see, sometimes it's the strength of the vibration. It depends on many parameters, the location of the vibration, and also on the amplitude, which you parameter which you put at the initial parameter in the component. Now, all of these examples, by the way, it's in the OptiSystem example library, which I'm going to show it to you later on. You can just try it yourself and see how it works. Here we show 3 vibrations and different locations, which are 20 meter, 40 meter, and 60 meter with different frequencies, 100 hertz, 400 hertz, and 500 hertz. In this example, we show 4 vibrations and the frequencies of these vibrations. In all these examples, again, the user would be, if you wanted, you can change the length of the fiber, the location of the vibration, the frequency of the vibration, and then study different parameters, condition, launching condition, which could give you the required results. And that would would be beneficial for the simulation tool. In this example here, this file, the Excel file, is experimentally measured data from the lab collected, and this data. What's happened is we analyze it using the interrogator of OptiSystem. So what you can do in OptiSystem component interrogator, you can load this data and then as you see here, what's happened is, because we don't have any other component here, just only the interrogator. And once you load the Excel file into the interrogator in the proper path, you give the proper path and name, and then you calculate using the calculate button. You're gonna have this trace, which represents the vibration location of the sensor, and then also the vibration frequency. Okay, so now I'm gonna go to the demo, which is again, it's if you go to the example library here under sensors, and you go PHI OTDR. Now PHI OTDR here, we have the examples, which is the 1 and 2 and 3 and 4 vibrations. And as you see here, this is the file where the results of the calculation is stored. Okay, so initially, if you download, let's say, for example, OptiSystem, after downloading OptiSystem into your computer, you don't see this file. This file will be created once you start to calculate the project. And this file, you can change its name, and then in the component, as we can see here in a minute, and then you should be able to store different versions of it. This file here is in the example to upload the measured experimental data. Okay, so now what I did here just ahead of time, because of the time used to calculate the projects. If you can see this project here, this is the component, the PHI OTDR component. And in this PHI OTDR component, you can set all these parameters as we described, the laser length in different units here. You can set up the laser line width, you can set up the fiber length, and so on. Okay, and once you do this setting according to what you need, you can do the calculation. And this calculation time depends on the length of the fiber, depends on the power used, depends on the number of vibration. So in this example here, we use about 100 meter. The length of the fiber piece is 100 meters. So it took about 17 minutes to run this example. That's why I calculate the example ahead of time. And here, just to show you the results in the interrogator. So this is, for example, the first vibration, second vibration, third vibration, and fourth vibration at the locations, which is set in the component, as you see here. So this is the locations, and this is the frequencies. So if you want to access the frequencies, once you close this, you can press on the frequency, and can you see the frequency at each location, the first frequency, second frequency, so on. Now you can zoom on it, you can adjust for example, the range of frequency, and then you can, for example, put this as 0, and you can download the results as well as if you want to download the image, and so on. So you can, similar to exactly OptiSystem, other OptiSystem visualizers. The other example which I calculated also just to show you is ahead of time, which took about 3 minutes. The other one took about 17 minutes, as I said. This one is only single vibration, and the length of the fiber, as you see here, it's 50 meters, and the vibration, only single vibration, located at 20 meters and with the frequency of 100 hertz. And this is 20 meter length, and this is the frequency vibration. If you zoom at it, you're gonna be 100 hertz. So if you say here, for example, 1 kilohertz, so this is 0.1. Okay, and again, this is the time. The results will be stored in the CSV file. If you look at the component here, you go component properties, you can see the setting the parameters of the component, the PHI OTDR interrogator. You can set the pulse repetition rate. This has to match the pulse repetition rate which you put in the interrogator and the component PHI OTDR, the fiber core index, and so on. So they match to be able to analyze these results, which is calculated by this file. The file name, as you see here, the CSV file, you can enter your file name, which for every calculation can be different, but it has to be .csv to be able to store the data of the calculation into it. Okay, now if you look at the data, if you look at the data here, which is calculated data, I have to open the file. This is the way how the data is stored. Okay, each trace is coming here, so this is the number of traces, and each column will be a trace, and it depends on the spatial length of the fiber and everything, how many sections you're gonna have. Okay, and you can post-process this, and you can look at the traces which we saw earlier in the presentation for each trace. Now this file here is the experimental data file. Okay, and this is the measured data, and if you go to the let's say here, the PHI OTDR Interrogator example, okay, you can see that we don't have any results here, but you can upload the file into it. This is the file, the path for the file, and then you can calculate the measured data into it. So you can click on it and take this is experimental data, and then press OK, and then you calculate. Now this is going to take some time to calculate because it's of the time of the complexity of the calculation. Okay, with this I conclude the presentation, and I'm open for question. Thank you for listening. Okay, so I'm going to take the first question here. It says, can you please comment on the market position? Who are the end users of the fiber optic vibration sensor relative to other sensor technologies such as piezo sensors and MEMS sensors and so on? And what are the main performance advantages and disadvantages of fiber optic sensors? Okay, so in terms of vibration sensors, you can use it for many applications. Like, I mean, you can have it on for civil applications where you can put it in, for example, on bridges, on in civil buildings, somewhere in the buildings where you wanted to monitor vibration. You can put it on the ground, for example, to see some users where they cross, let's say, a certain area for military application. Let's say you can deploy the fiber, anyone walk on it, create some vibration. You can check with some kind of, for example, sensing sensitivity control. You can control the strength of the signal. You can do some kind of more development to apply it for military applications. The other types of sensors, let's say, for example, MEMS or other types of sensors, this is the applications. It's going to be different. Like, I mean, the MEMS can be used for different applications, and we are actually at this moment we are also developing a component for MEMS, which is hopefully going to come if not in the next release, it will be mid next year, which you can use it for directing light in different positions and control it, use it for free space optics mainly. So the application from the piezo sensor, like for example, it's different than the fiber sensor. Fiber sensor allows you, for example, to use long distances between the sensor location and the monitoring station. As we said, you can use it for distributed sensor, which you cannot use piezo electric elements for that purpose. You can put it in a certain location, but you have to have a means to transmit the signal, because the signal would be not optical, would be electrical after the piezo electric element, if you detect it. Okay, another question here. It says, how to define the extinction ratio of the pulses. At this time, is inside the code, we set the extinction ratio to 30 dB. We're going to allow the users to adjust the extinction ratio in the next release. Another questions here we have about the release. When is the expected date for the OptiSystem 17? We are expecting it to be sometimes before OFC, which is in March. So hopefully we can release this OptiSystem 17 in end of February or mid-February. That's the target at this moment. Another question here, it's about the coherent detection. So the PHI OTDR right now is used based on direct detection, but coherent detection is not considered in this product at this moment. Okay, so with this, at this time, there is, if there is no other question, I'm going to conclude the webinar. And as Josh was talking, we're going to send the a recording of the webinar shortly after some time today to all webinar registers. Thank you very much for attending the webinar.
Thank you for tuning into this live webinar. We will be emailing a link of the webinar to everyone an hour after the presentation. We also encourage anyone with any questions about our software or anything from this presentation to email us at support@optiwave.com. We appreciate you attending this webinar. Have a good day, everyone.